Today we are introducing logs. So this little slide talks about why in the world do we need these silly things? Just like we need division to undo multiplication problems and subtraction to undo addition, we need logs to solve exponential equations. For example, whenever we have an x in the exponent, for example, how long until my account grows to $5,000? If I put in 2,000, it's growing at a rate of 4%, so I multiply by 1.04. How many times or how many years do I need to leave it there until it'll grow to $5,000? That would require a logarithm, okay? For how long until the population reaches a certain value or a radioactive decay gets to a safe level, etc. Those are the situations for which we need to solve for an exponent. So we will need an inverse operations, and that operation is called logarithms. So real quick review of rational exponents. When you have it's easier to read maybe on this one. If you have a to the b over c, the c, the number on the bottom, is the radical, and the b, the number on the top, is the exponent, and you can do it in either order, okay? You can take the radical first and then do to the power, or you can take the power first and then do to the radical. For example, 4 to the 3 halves. You could cube 4 first and get 64 and then square root it and get 8. Or you could square root 4. Let me see if my pen is working here. You could square root the 4 first and get 2. Whoops. And then 2 to the 3rd would also be 8. Okay? These are not real complicated ones, but this 25 to the 1/2 means the square root of 25. So the answer, anybody? 5. Okay. This means the 5th root of 32. See if you can find 32 under powers. Okay. This is 2 to the 5th. It's on that little sheet. Does everybody see what I'm talking about? Powers of 2. Okay. 4th root of 81. Anybody know? Whoops, 81, not 84, sorry. Anybody see 81 on that sheet at all? It's 3 to the 4th, so the 4th root of 81 would be 3, right? And negative 8 to the cube root, does that work? It does because it's a cube root, right? So you can have a negative number. So this would be negative 2 times negative 2 times negative 2 would give you negative 8. We okay? All right. So the learning targets you're going to have to do eventually are graph and analyze graphs of logarithmic functions, okay? Those are the inverses of the exponential functions we did the other day. So in the past, when I made students do it without a calculator, you pretty much had to graph the exponential and figure out what its inverse would look like. I'm going to let you use a calculator, and I'm hoping these calculators have log base on them. Otherwise, we're going to have to do something to make it fair because the other 3 classes I teach all have calculators with log base. Okay, I can rewrite from log to exponential and exponential to log. This is huge. This is the basis of all of this, okay? If you don't understand how to go back and forth, then this is just going to not make any sense. I can evaluate logs with and without a calculator. I would prefer you try without today for most of these. I can find the inverse of a log or exponential equation. That we're going to deal with later, okay? That's not on today's plan. So this was an exponential what? Growth or decay, this black line right here? Yeah, this was an exponential growth. So the log would be the inverse. Do you guys remember that an inverse means it has to reflect across that line y equals x? So this ordered pair, does anybody remember where it always crossed at? Yeah, 0, 1 would become well, if I could hit it, there we go, 1, 0, okay? And this had a horizontal asymptote, the growth one did, of x equals 0. This one is going to have a vertical asymptote of y equals 0. Any log graph will have a vertical asymptote. It's the big difference between exponential and log. Okay. A logarithm or log, I'm going to sneeze. Sorry. Oh, thanks. Is another way of writing exponents. So log base b of a equals x is another way of saying b to the x equals a. The answer to a logarithm problem is the exponent, okay? And again, this one over here reads log base b of a equals x. Now, I'm going to show you a video, and they use a little bit different letters, and I hope it makes some sense. This also just introduces the idea that a log base 10 is called a common logarithm, and whenever you see this, you have to understand that it's base 10, okay? So this is just written log of x, and what that means is 10 to some power equals x. And we're going to try to find the power. All right, we're going to try this. I did not test this before class, so I don't know if we have sound, which will be the most important thing. Well, this... what is happening? Okay, I would like you to go away. I can just about do this word for word because I've shown this so many times, but it's kind of pointless. Didn't work. For great amusement, maybe I can play it another day, but if I can get it to work. All right, so the inverse relationships between logarithms and exponentials can be used to evaluate logs. So here's what it said in the video. It said log base b of some number n equals p the power. I like those letters because it helps us remember where they go, okay? Log base b of some number equals the power, means b to the p equals n, okay? Everybody, you're going to be able to do that because that's most of the lesson right there is going back and forth between those two, okay? That you got to memorize. These are a few additional properties of logs. So this one is saying b to the 0 equals 1. Did we discuss that on Friday? Anything to the 0 power is 1. So anytime they have the log of 1, it's just 0 no matter what b is. By the way, I should have, when we discussed logarithms, you can never take the log of a negative number, okay? It says if you try to take the common log of a negative number, your calculator will give you an error. So the log b has to be positive, and so does n, okay? P can turn out to be negative, but the b and n have to be positive. This is saying b to some power equals b to the first. So what would that have to be? Just a 1, right? So the log base b of b is 1. They just want you to understand when you take log base, it's saying b to what power is b would be 1. So as long as the base and the number are the same, it's just 1. This is the same thing because this is 1 to any power. This has to do with properties we're going to learn tomorrow. This is a little confusing, but basically this x can move out front, okay? Yes. Yep. This is saying b to some power over here equals b to the x, so it's true for any number, x, okay? So log base b of b to some power, the answer is just the power. And the same here, the b and the log base b undo each other. They're inverses, so you just get x. And it doesn't matter if it's base 10, if it's base ln, natural base, okay? These are the two on your calculator. Did everybody find those two? Log is base 10. So when it doesn't say what base on your quiz and it says log, look at the key, it says it's base 10. If it says ln on your quiz, the base is e, which is probably the next slide. Nope, not quite. Okay. So how do we rewrite this as an exponent sentence, guys? I'll put it at the top again. Log base b of a number equals p the power, means b to the p equals n. So this would be 14 to the y equals x. The answer to a log is the power. So this one means what? 17 to the second equals 289. Let me tell you, I'm more likely to put number 1 on a quiz than I am number 2, because most of you can logic through how to write number 2, right? But number 1, you have to understand where things go. What about this one? This means log, what's the base? Well, what was the base here? A, yep. And of the number equals the power, so it's of b equals the power. So this would be log base 7 of 1 over 343 equals negative 3. Whoa. My pen is getting worse. All right. You are going to have to do some of this kind of stuff, okay? This has to do with negative exponents, putting it in the denominator. We talked about that Friday. So this means 343 is 7 to the third, but the negative part was because it was in the denominator. All right. Evaluate, these should be done without a calculator. So this is very similar to what we just talked about. This says 5 to some power equals 1 over 25. Well, 25 is what power of 5? 2. What would make it go to the denominator? Yes. So this is negative 2. Okay. 5 squared is 25, but to put it down in the bottom would have to be a negative power. All right, we did this at the beginning of the lesson today. Did anyone notice 3 to what power is the square root of 3? Do you remember? Yes, do you remember right here? Square root of 25 is 1/2 power. Okay, this is what we're talking about. The cube root would be the 1/3 power. Everybody got it? Okay, so this was the 1/2 power. That's all they're looking for, is what power is it when you do a square root. All right, anybody remember the rules we just went over? This is just 1, means 7 to some power is 7, would be to the first. What happens when a log base 10 and a 10? They undo each other, so you just get a 5x. So I think this is supposed to be 2. Does that look like 3 to the log base 3 on yours? So that's supposed to just be 2. All right, this one you have to know. 6 to what power is 36? Okay, this one's going to take a little work. 3 to what power is 1 over 81? Well, if I move it to the bottom, I have a negative power, right? And what power of 3 is 81? 4. So this is -4. Okay. This seems like we need a calculator, but this is actually log base 10 in the exponent power, so they would undo each other and just be 13. All right, a logarithm with base e is called a natural logarithm. Remember, e was that, anybody remember approximately what e was? 2.7 something? Yes, okay. So log base e is just written ln of x, okay? And it means e to what power is x? But it's written ln, it's not usually written log base e, okay? There's a shortcut. All right, so let's practice a little more. So again, log base b of n equals p means base to the power equals n. So how do we write this? What is the base, number 25? ln means the base is e. The answer is the power, so 4 equals x. And we don't need to go any further. They just want us to rewrite it. So somebody tell me what this one would look like. Yep. Okay, rewrite as a log. When we see e to some power, instead of writing log base e, we write ln. That takes care of the base. Oh, this pen. Natural log of 50 equals, remember the answer is the power, so equals x. And this one, the answer is the power, so we'd have ln of x equals 0.5. Is that what that says, guys? Okay. These you got to do on your calculator. Okay. ln 64. I don't have my calc. Yes, I do. I had this one. ln of 64, quit, Hochbauer. 4.159. It doesn't say how many places. ln, everybody finding it? It's just 2 above on. Natural log of 1/3 is negative 1.099. Okay, why is that one negative? Yeah, less than 1. So it's 1 to some negative power, moved it to the denominator. All right. These are the same properties we talked about a minute ago. This means e to the 0 equals 1. So anytime you see the natural log of 1, it's just 0. ln of e, this shows up a lot, okay? The natural log of e is just 1 because it means e to the 1 equals e, okay? This is saying base e down here, e to the 1 equals e. So when you see ln of e, you need to know it's 1. That's a big one. Natural log of e to the x equals x. Okay, they just undo each other. Same here, okay? All right, so what's happening here? ln and e undo each other, so the answer is, or if you think of this as base e, the answer would be e to something equals e to the 7th, so it's just 7. All right, part B, anybody? 5, part C, it's just an x squared, yep. All right, now this is what I'm hoping you have on these calculators. Can somebody go to the math number and then go way, 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 way to the bottom? Does it have log base? Okay, and when you hit log base, so you go math, I usually arrow up because it's closer, and you find log base, does it let you type in those little boxes? Okay, whew. So if we had log base 2 of 64, was that 6, guys, when he did it in the video? Yay. Okay. Means 2 to the 6th equals 64. That button is going to be your saving grace this year because in the past I made students take a quiz without a graphing calculator, and so you could not do that log base button. Most calculators do not have log base button, and we'll talk about how you would do that. There's a formula called change of base that doesn't need that button. You would have done log of 64 divided by the log of 2. Yeah, change of base is used in chemistry, maybe. Okay, you should have maybe done some of this in algebra 2 as well, I don't know. But I'm going to let you use that log base button. If you have an older calculator, like for homework, you may not have this button. If anybody, did you use a Chromebook emulator last year? Your Chromebooks came with a TI emulator on them. If anybody wants that for their Chromebook, we have licenses for a few, but like 360 for the whole school. So we were really stingy with them at the beginning of the year, and like only 15 people have activated a license. So if you would like one, I have plenty. Let me know if you want it on your Chromebook. Okay, so we're going to try to do this without a calculator. What does this mean? Log of 49, 1/7 means 49 to some power equals 1/7. Well, what power of 49 would get us to a 7? The square root, but what's the square root? Power, 1/2. Okay, so this would be 49 to the 1/2 is 7. What would move it to the denominator? So this is negative 1/2. Okay, this one's tricky. 32 to some power equals 2. Well, normally 2 to the 5th equals 32, I think, right? Is that on your sheet, 2 to the 5th? So how would we go backwards? 1/5, because we'd 5th root it, okay? All right, so this one is 1/4 to some power equals 64. Now, we need to make it a 4, so that would be a negative, right? To flip it back over and make it a 4. And then if you look on your sheet, are 4s on the sheet at least a little bit? What power of 4 is this? 3. So what is this? We had to flip it over and change it. It would be negative 3, yep. And again, I'm not taking your calculator away. All right, 18 to some power equals 124. Is that something you can do on a without a calculator? No. So can you, if you had an old calculator, you would have had to type log of 124 divided by log of 18. But you guys should be able to do the change of base. So you go math, arrow up to log base, and the base is 18, and the number is 124, and we wind up with 1.6677, 1.6677, I don't know. Anyway, something like that. Did someone else get that? Okay. ln of 12, that one's definitely a calculator. Did anybody type that one? Natural log of 12, someone give me a couple. And log base 9 of 63, I don't know what power of 9 would get me to 63, so I'm going to have to do that one on my calculator. Again, I'm just going to see if I can go back in and type in here. Was it 9 and what was the other one? Does that look right? Log base 9 of 63, 1.886. All right. Then I have extra practice on this kind of stuff, but I'm going to skip all the way to graphing so we don't run out of time. All right. We have to be able to graph these. Now, without a calculator, what you would have done in the past is first graph the power. So 10 to the x. Guys, tell me some powers of 10. If you put in a 0, 10 to the 0 is 1. 10 to the first power is 10. 10 to the negative 1 power be 1/10 or 0.1. So it's looks like this. That's what we learned about on Friday, okay? With an asymptote here. Well, what does the logarithm do to those ordered pairs? If it's an inverse, it does what? Yes, it flips the ordered pairs. So over at 1, we're at 0. All the way out to 10 before we get up to 1. And at 1/10, we're already down to negative 1. So a log base 10 looks like this with a a vertical asymptote at x equals 0. To graph a logarithmic function, you can use the inverse exponential function and then invert the values from the table to graph the log function. All right? Or you can use your calculator. All right, so just real quick, a log normally with a normal base b greater than 1 looks like this shape. But if you had a little base like log base 1/2 of x, it would actually be a decay, logarithmic decay, which we don't use very often because most of it's negative, okay? The thing to realize is that both of these have x equals 0 as their asymptote. What about domain and range? That's really about all I care. Oh, and increasing and decreasing. What's happening, guys? Domain is like left to right, yes? And range, there's an arrow on both ends. This is all real numbers. Everybody okay? And this one is increasing and this one is decreasing. All right, so log base 3, you can try it on your calculator. It looks like this. What is misleading about this graph? Again, you would go to y equals, and you would put in, let's see, I'll do mine in pink. You would go math, up arrow to log base, put in a 3, and then x, log base 3 of x, okay? I'm going to have extra ones on here. And if you do a zoom 6, okay, it's my pink one. But does it look like it stops? Does it stop? No, it just gets so close to that x-axis that it doesn't look like it does anything. Okay, so it does have a point at 1. And if you went out to 3, it would be up to 1. Anybody know another power of 3? Log base 3 of 9. Anybody know what power that is? 2. So by 9, is that the very last one, guys? It would be up to 2. It's growing very slowly. Unlike exponential growth, which grew very quickly. Domain would be 0 to infinity. Range would be negative infinity to infinity. X-intercept was 1, 0. The asymptote is the x-axis, the y-axis, just kidding, which is x equals 0. And it is increasing only. As you get closer to 0, the y values are getting more and more negative. As x gets incredibly big, the y values are also getting bigger. Okay? Any questions on any of those properties? X doesn't ever go towards negative infinity because it can't be negative. All right, a log base 1/2 looks more like this, and I'm likely to not ever put one on a quiz or test. Okay, it would go through 1 here. It would go up here by -2. Let's see. 2 to what power is 1/2? Would be 2 would be at -1. One, 2, 3, 4. I think by 4 it would be down to -2. By 8 it would be down to -3. 0 and up, all real numbers. X-intercept is still 1, 0. The asymptote is the y-axis, which is x equals 0. And it is all decreasing. And I don't care about end behavior. Okay, I don't think I'm going to ask you one of those, period. All right, we want to talk about transformations for a second. If you graph log base 2 of x, okay, at 0, it's at 1. At 2, it's up to 1. And at 4, log base 2 of 4 would be 2. At 8, it would be up to 3. So it looks like this with their funky graph paper. They've really stretched up graph paper. Does everybody see that? It's counting by halves going up, okay? Then can anybody tell me what, I don't care about all this other jazz they want to know, but can anybody tell me what 2 things happened here? A negative on the whole thing would be reflect over x, okay? Right 1, okay? So if we reflect over x, the shape is going to go this way. The right 1 means our asymptote is now at 1, and our intercept is now at 2. And this point that was at 2, 1 would have gone to to -1, to -1, and then to the right 1. Yes. Okay. Sorry, my brain took a moment. All right. I'm not going to make you graph transformed ones. You may have to do them on Delta Math, but you can use your calculator, okay? You can use your calculator. You can use the table to find points. Here are some more. This is a straight up left 4. See how it just moves the asymptote? Okay, this one is a stretch, so it changes, and then left 2 went up a little faster. All right, can anybody tell me these? Yes, reflect over y. And at the back, not in with the x, would move it up 3. This is a vertical stretch. Now this is tricky, but because there's no parentheses around the x and the 1, you have to assume that the 1 is on the outside. So this one would be down 1. All right, so the homework is in Delta Math. Try to do it without a calculator, okay? I will write myself a note right now to post in the stream the link to request the Chromebook emulator, okay? How many people think they would like that on their Chromebook? Couple? Okay. It is a form. You have to fill out the form, and then by tomorrow you'll be granted permission to use it, and then I can show you how to actually get it on your calculator, your Chromebook, okay?